question here, again, is not predicting the products. The products are already given. It's not one, it's many. What this question is asking is explain how each of those products is formed by mechanisms. There are, it could be more, but the 4 products is shown with these reactions. And then we want to explain how each one of these 4 are formed by following the mechanisms. So you have to look at the reaction conditions. We have an alkyl halide. This alkyl halide is a bromine sitting on the carbon that only have a 1 carbon substituents, even though it's a cyclobutyl bigger, but just 1 carbon directly connected to that carbon-bearing halogen. So you call this primary alkyl halide, right? That's a primary alkyl halide. And then we have a reagent, methanol. And then this little triangle mark, that actually is a very, this is a symbol for the heating. Well, this one thing I forgot to mention that is E1 elimination process needs a carbocation formation. And then carbocation is not a stable species. So the molecule needs a little bit of the motivation. So that motivation comes as a heating. You provide heating, that is, you increase the energy in the molecule. So halogen can pop out easily. So heatings are not necessary, but if you do heat, it makes an SN1 reaction or E1 reaction goes better. So if the heat sign is given, you should consider E1 and SN1 can go faster, but does it mean that E1s always happen with the heat? No, SN2 reaction also go faster with the heat. E2 elimination reaction also go faster with the heat. So heat does not really tell you this is an E1 SN1. It's not that straightforward. Heating basically makes every reaction go faster. The other reaction, SN2, it is fast no matter what, so you don't have to heat. But E1 elimination reaction or SN1 reactions is a slow. So the heating can make a big contributions. So that's what people tend to heat. But heating is not the indication, sole indication of which mechanism take place. So sometimes in E1 SN1 reactions, we provide within the question without the heat. And you still need to figure out that's an E1 SN1. But if you see the heat, that's kind of that makes it more positive. So you can figure out easier. But anyway, the why this was that SN2 is in the answers is in the reagent used. Primary alkyl halide is a really great substrate for an SN2 reaction. If you remember that SN2 reactions is a really sensitive to state hydrogens. So the primary is better than secondary, secondary is better than tertiary. And this is a primary alkyl halide. So this is really good for the SN2 reactions. But we're not going to have an SN2 reaction with this because reagent we see is a methanol. That's a neutral alcohol. Oxygen has a lone pairs. But when oxygen is a neutral, these lone pairs are not nucleophilic, not basic either. That's the reason I keep telling you, when you drink the water, you don't die. Because water is not base, water is a nucleophile. The neutral water, do you ever have a temptation to use it as a strong base or strong nucleophile? Think about the water you drink, then you probably think, again, it's not a strong base, strong nucleophile. So SN2 is not possible because we don't have a strong nucleophile. But this weak nucleophile still being able to work if it makes a carbocation. So that's why these reactions are happening SN1 or E1 through the carbocation intermediates. Because a faster reaction like an SN2 cannot happen because we don't have that strong new reagents is required for the SN2. Anyway, these are the processes that we're going to go after we finish all the components. But for this one, bromide will fall out because nothing will happen to that. And then you're going to get the carbocation. So this carbocation that initially formed is a primary carbocation. And then we talked about the stability of the carbocation. Primary is the worst. Carbocation electron depletion species is it needs some help to get stabilized. The more carbon substituents the carbocation has, the better, because the carbon substituents are electron donating groups. It can really alleviate a little bit of the electron deficiency by donating its electron density to the bond. So the primary carbocation is really, really bad. They really don't want to form. Once it's formed, then they will try anything to make it stabilized, which including rearrangement. So there are hydrogen in the adjacent carbon. This hydrogen shift happens really fast. So that makes this carbocation move here to there. So that's a tertiary carbocation it can form right after rearrangement. Then, in order to make this product, we have to have an elimination done. That proton on this carbon, now taken by the base can pick up this proton, and then double bonds formed. That's how these things made. I mean, obviously, right after formation of the primary carbocation, if the proton in the tertiary set are taken by the base, then you can form the same product before the rearrangement. That path is possible. But I think that path is less likely compared to this one, because right after the primary carbocation forms, it wants to release the pressure by making this hydrogen shift. This hydrogen shift is going to be a lot faster than the sorbon molecule, and the sorbon molecule travels there and pick up the proton as a base. So I think this is the most likely happen, not this direct route. But small fractions may happen this way, and this molecule, this product, can be produced by really two different pathways. But I think these are more likely way to make it happen. Anyway, that's a double bonds out of the ring, and that's this product. This carbocation that's rearranged can be captured by the solvent if it acts as a neutral valve. Then you get SN1 product. So this is an E1 product, that's an SN1 product. You can imagine that, how this happens. But that's with the same four-member ring you do see in the starting material. But there are other molecules, other products are made, but that other products now have a five-member ring, not the four-member ring. So how come the four-member ring change it to the five-member ring? So that is something else that you need to figure out. You need to look at this rearrangement process. The rearrangement, hydrogen is a lot easier to move. But I told you, hydrogen is not the only one that can move. Carbon can move as well. It's a little slower than the hydrogen. I mean, it's actually a lot slower than the hydrogen, but it can move too. But when this carbon shift, basically you are making bond between these two, and you're breaking the bond here. So that makes a 1, 2, 3, 4, 5-member ring, which is shown right here. And that's the carbon now becomes a carbocation. So it makes a 5-member ring by the methyl shift or the carbon shift. And this time, I would say this methyl shift or methylene shift is a faster than usual. Faster than the other example I have given you. Why do you think I say that? Yeah. It was starting from the 4-member ring, which is a ring constraint. 90-degree bond angle is not ideal. But when this methylene shift, it makes a 5-member ring, which actually much better. Because then all the bond angle can be most likely tetrahedral. So that's a huge incentive for the molecule to move the carbon. So most of the time, carbon shift is slow, but this example, I don't think it's slow. I think it's almost as fast as a hydrogen shift because it can release. It can release the. I mean, it can basically make this carbon tetrahedral by making a 5-member ring. But anyway, so this methylene shift make a different carbon intermediate. It's a secondary carbocation. Obviously, that's not as stable as a tertiary carbocation, but this is a ring-strained tertiary carbocation. It's a secondary carbocation without the ring strain, so it's hard to compare which one the better or worse. I would say that this process is going to be as efficient as the other one. So different carbocation forms by making different things move, then now that's going to be subject for the SN1 reactions or E1 reactions. As for the E1 reaction, base, which is the sodium molecule, come pick up the proton in adjacent carbon. This carbocation has two adjacent carbon, one here, one there. But why am I only taking the proton only this side? Because the molecules are symmetrical. So it doesn't matter which side they pick up the proton, it will make the same products. So this comes pick up this proton, make a double bond between these two, and you're going to have this elimination product, that one, which was made by the E1 elimination reaction through the rearrangement. That carbocation, rearrange the carbocation, captured by the nucleophile, which is the sodium molecule again, then you're going to get SN1 product. You can see that the SN1 reaction, E1 reactions can happen at the same time because they go through the same intermediates. It's really hard to put one over the other. I mean, there are ways to narrow one over the other, but we're not going to talk about right now. So, but most of the time, they both will happen at the same time. Both can be complicated by the rearrangement too, because they have the same carbocation. So this is a very mechanistically rich problem. You should be able to keep thorough for all the way to the end for every possibility. So this is something that you should prepare yourself. All right, so that is kind of showing you, these reactions that can be complicated. And then let's talk about some of the problems. What this question is asking, give me the SN1 E1 product. I mean, right now, we are just learning, so I'm narrowing down which product I want for each question. But when you look at the practice test, you're not going to find this in direction anymore. In the test, I just give the reagents. You're supposed to figure out what product you are going to give me. SN1, E1, E2, or SN2, depending on what you think is likely to happen. So it's going to be a lot of decision making that you need to do. And we're going to talk about that next class. But right now, we're going to focus just SN1, E1. I kind of narrowed down. But it's basically the same reason I give. So first of all, one methyl cyclopropane and cyclopentane. I hope you know what the structure is, right? The cyclopentane, I'm bringing one iodine, one methyl. So both are on the same carbon. That's the tertiary alkyl halide, right? Tertiary alkyl halide, really bad for the SN2 reactions. So even though we have a strong reagent, SN2 reaction cannot happen because this is really bad for the SN2. At the same, regardless, we don't have a strong nucleophile anyway. We have something called the methanol, and I keep saying to you, the neutral alcohol or neutral water are not a good nucleophile, not a good base. So there's no way you can have an SN2 reaction with this weak base or weak nucleophile. So this is definitely not going to stick there. Only thing can happen with this weak reagent is SN1E1. So what will happen first? It's going to stay in the solution for a long time. But if there's enough heat is there, or enough energy in the molecule, then halogen pops out, then you get the carbocation. Once the carbocation forms, the first thing that I ask you to do is figuring out whether it's going to be rearranged or not. That should be the first thing you need to do. This is a tertiary carbocation, right? If you make the adjacent hydrogen move to there, then you're moving the carbocation there. That makes a secondary carbocation, which is the last state. So now moving that direction. You may think about moving the hydrogen on the other side. This methyl hydrogen, the methyl groups move over here. Then you get the primary carbocation, which even works. So what that means is rearrangement is not going to happen. This is a tertiary carbocation, the most stable form it can be, then it won't bother to moving at all. So don't just try to rearrange for no reason. It only move when it becomes a stable carbocation. better carbocation. So anyway, so this is not the subject to move. So it will go through the process of the substitutions at the same time elimination. The sulfur molecule, it behaves as a nucleophile. It basically, the lone pair of the oxygen capture the carbocation, then the proton of the alcohol lost. That's what this minus H plus means. I kind of condense the third step together there, because I will do another step. But anyway, this captures and this proton goes away, then you get the SN1 product, right? That's an SN1 product. A sulfur molecule can come as a base. If it comes, pick up the proton from the adjacent carbon, this adjacent carbon, then you're going to have a double bond between those two. That will be this product. Question is that the only elimination product? For the SN1 product, yes, there's only one. But as for the elimination product, this is not the only one it can be made. Because this carbocation has an adjacent hydrogen here, and then you may think that there is an adjacent hydrogen there, but this hydrogen is equivalent to that one by the symmetry. So that does not make another product. But what makes another product is hydrogen on this side. The hydrogen on the methyl groups, if that was taken by the base, then you get a double bond between those two, you make that product. So it actually makes a two E1 product. One SN1 product and two E1 product. The question is asking you to give me the SN1 E1 product. So you are supposed to give me all three. But I can take this question further. Which one is going to be the major product? Which one is going to be the minor product? So there's only one. Let's talk about between those two. Those two are elimination products. How can we figure out which ones are major? Is by looking at the carbon substituents. Right? The number of the carbon substituent double bonds, that's the what determines the stability of double bonds. More stable double bonds makes the most stable products. So this double bond is a two hydrogen here, but there's two carbon on the other side. So these are di-substituent double bonds. That double bond is a 1, 2, 3 carbon substituents. It's a tri-substituent double bonds. So that one's the most stable. So between those two, which one's going to be more stable? The more substituent double bonds. So we are expecting that one is going to be the E1 major product, and that's going to be E1 minor product. So I will probably see more of this compared to that. But can I compare E1 and SN1, which one's the most stable? You cannot, unfortunately. The experiment you can do and you can find out, but the thing is we cannot easily predict which one will happen more between the E1 and SN1. So we're not even trying to get into that silly debate. So we're going to say that both E1 and SN1 will happen at the same time, about the same amount. In reality, it may be different, and it may be different in each cases, but we just cannot be making general assumption. So only thing you can say, between the E1 products, we can say which one's a major or minor, but we don't want to say SN1 is a major or E1 is a major. We cannot do that. So that's something that I want you to do. Question? All right, so that's this question. Next one. 3-bromo, 2,2-dimethyl butane, if you draw the structures, that's this. That's a secondary bromide right there. Before I get there, this is something that you probably forgot, but I'm trying to remind you. Maybe this is not the right I thought about, but we see this already. It's a secondary alkyl. If you look at the SN2 reaction, primary is the best because it's not stably heated. Still, the secondary alkyl can go through the SN2 reaction. Tertiary is just too bad. You don't see the tertiary alkyl for the SN2 reactions. But secondary, yes, SN2 can happen too. This molecule have a bromine sitting on the secondary carbon. So if I have a strong profile, can you expect SN2 reaction with it? Most likely, yes, right? Unless you have a tertiary butane groups right here. This is something that I told you, it's kind of very exceptional case. If you have a tertiary center next to the, whatever the carbon, this could be primary, this could be secondary, but if you get a tertiary center right there, this has a big presence over that, and that makes SN2 reaction still not going well, even for that molecule. But this is a really bad substrate for the SN2 reactions, even though it's a secondary. So sometimes the people forget that part, so I'm reminding you. But anyway, these reagents are not strong nucleophile. There's no way you can expect an SN2 reaction. So this is kind of a silly assumption. I'm just trying to make the, the case. In case you have a strong nucleophile with this, still SN2 reactions are not possible. But this is a weak base, weak nucleophile, neutral, alcohol, and solvent. So it's not the subject for the SN2. This is basically going to go to the other mechanic.
Is this only true if it's a tertiary next to a secondary, or if it's a tertiary next to a primary?
Even tertiary next to primary is not good. It just proving some, requirements makes it difficult. Yeah. All right. So then what happened was the bromine will fall out with a pair of electrons. So you get the carbocation there. That's a secondary carbocation. It can be better, right? But the thing is, then you need to move things, in the from neighboring hydrogen. You can see that there is a hydrogen in that position. If the hydrogen shift happens, then this carbocation will go to that end, which will become a primary carbocation. So this is definitely a bad choice. So the molecule is not big enough to do that. If you look at the other side, there's no hydrogen. This has a carbon, as a methyl groups, no hydrogen. So no hydrogen shift. So if you stop there because there's no hydrogen can move, then you're forgetting that hydrogen is not the only thing that moves. You can also make the carbon move. It's a little slower, but it can happen. So if this carbon moves, then now you have a tertiary carbocation, which is a lot better than the secondary carbocation. So that's the reason the carbon shift can happen. Because it makes a lot better carbocation. So that's a huge incentive for the molecule to do this. So that's the major carbocation between these two. And then that is going to be the subject of the SN1 and E1 product. So as you see, before even I talk about SN1 E1, what I need to worry about first when I see the carbocation, will it rearrange? That's the first thing should pop in your mind. As soon as you see the carbocation, not E1, not E2. It's a very inherent problem with the carbocation. It just happens. All right? Even after this test is done, you still going to see the carbocation for other reactions. And then as soon as you see the carbocation, same thought has to come to your mind. Will it rearrange? So anyway, it rearranges. Now this one will go through the two process. First, it can go through the substitution reactions, but the thing is, we have a solution. We got two carbocation species. One is a rearrangement, one is the original one. The original one still have a finite lifetime. It may be short, it exists. It's not like it doesn't exist at all. It automatically rearranges. I mean, it automatically rearranges, but that means it takes a time to move the carbon. Even the hydrogen shift takes time. The carbon shift takes even longer time. So those two will kind of hang in the solution together. We got the majority this way, but still you got the minor carbocation still there. So if you are asking to get all the product, then you are still supposed to think about minor carbocation before the rearrangement that may go through the SN1 reactions. And that can also go for E1 elimination too. But anyway, but as an SN1 product, I'm expecting this capturing the more stabilized carbocation is a major product because it's coming from the more stabilized carbocation, which is a majority in the solutions, and the solo molecule capturing this major carbocation should be the major SN1 product. So in this case, we can say between these two possible SN1 products, which one is the major, which is the minor. I would say that will be the major, this will be the minor, because more stabilized carbocation will be formed more, and then that will lead to the major product for the SN1 product.
What is the, set on the bottom one, is it in that area, there's no way for it to come inward on the cation?
No, that's basically when the nucleophile make a reaction. Carbocations are flat. It's not sp3 hybridized. So there's a definitely space for things to come in. It's different from the SN2. And that's just SN1 side. Then now we need to talk about the E1 elimination reactions. And we got two different carbocations. So potentially we have to go for the E1 reaction with this, we have to go for the E1 reaction with that, and we know this is going to be the major components, more likely, more things will happen with that. But let's just be thorough, as I said, thorough is something that I'm expecting from you. So this carbocation, the original one, if it goes through the elimination reaction, which means this proton is taken by the base, you got double bond between those two, and that is definitely the E1 product, because when you lost the proton adjacent to the carbocation by the base, then you get the elimination product, that's the E1 product. But that's not the only one. That one can have this proton lost, and you're going to have a double bond made between these two, which is this one. Is that the only E1 product, those two, then there are actually one more. There are hydrogen on that carbon as well. This carbon has a hydrogen. When the base come, pick up this proton, you're making bond between those two, double bonds there, which is that one. So in total, you have a 3 E1 products made. Which one of those 3 is a major E1 product? Well, then you need to think about the alkyl substituents on double bonds, right? This one, this double bond has a 1, 2, 3, 4 carbon substituents. That double bond has a 1 and 2 carbon substituents. So between these two, I would definitely choose that one as a major. But why not am I even compare that one? That's coming from the minor components. So that's the minor. Oops. So that's the minor of the minor. So I would probably say that this with a major E1, that's going to be the minor, and that's going to be the minor of the minor. So if I rank the which one you do see the more, this will be the most, then the second most, then will be the third most. But I don't compare between SN1 and E1 because that's a silly question because I cannot even answer that. But as between the SN1, between those two, I can say which one's going to be major, which is a minor, because these are more stabilized carbocation, so that will be weight more. It will lead to the better, more products. So SN1 products from the rearranged carbocation, that will be the major product. And then this elimination product still is a major product because it's coming from the major carbocation, but this is a more substituted part, so more substituted double bonds are made.